I'm going to talk about minimum weight dominating set in graphs of bounded arboricity. This is work I'm doing for my PhD at the University of Waterloo under the supervision of Johan Kahneman. In the minimum dominating set problem, we're given a graph G, vertex set V, edge set E, and weights WV on the vertices. Denote by N of V the neighborhood of V for vertices V. S is a dominating set for G if the union of V and its neighborhood contains a node of S for any vertex V. The minimum weight dominating set problem is the problem finding a dominating set of G of minimum weight. Minimum weight dominating set has an nth harmonic number approximation where n is the number of vertices. This is by reduction to set cover. It is NP hard to approximate minimum weight dominating set to within 1 minus epsilon ln n for any epsilon greater than 0. Lenson and Wattenhofer proposed studying minimum weight dominating set on quote unquote locally sparse graphs. So what does locally sparse mean? We say a graph has arboricity A if A is the smallest number of forests, F1, F2, all the way to FA, for which its edge set can be partitioned into. Here in this graph, its edge set is partitioned into the red forest, the blue forest, the black forest, and the green forest. A graph has arboricity A if and only if the number of edges of the graph induced on S is at most A times the size of S minus 1. In this way, bounded arboricity is equivalent to locally sparse. A previous result by Banzel and Ambo is that unweighted minimum dominating set admits a 3A approximation on graphs of arboricity A. They also show it is NP hard to approximate minimum dominating set to within A minus 1 minus epsilon for any epsilon greater than 0. Their algorithm works by LP rounding. Dvorak 2017 showed the algorithm actually achieves a 2A plus 1 approximation. The natural LP for min weight dominating set has a variable xv for each vertex v, which is set to 1 if the vertex is in our solution set S, and 0 otherwise. The LP is to minimize the weight of the selected vertices subject to selecting at least one vertex in the closed neighborhood of V for all vertices V. The closed neighborhood is just the union of V and its neighbors. Our main result is that the natural LP for min weight dominating set has an integrality gap of A plus 1 in graphs of arboricity A. Our approach is based on the primal dual method. We start with the zero dual solution, empty solution set S. While S is not a dominating set, increment all dual variables YV for undominated vertices V, maintain dual feasibility. When a dual constraint becomes tight, that is satisfied with equality, add the corresponding vertex to S. At the end, reverse delete, that is consider the nodes of S in the reverse order they were added, and if we can delete the node and maintain feasibility, we do so. It's a focal result that if for dual variables YV, that we increase, the closed neighborhood of V contains fewer than alpha hit solution nodes on average, then we get an alpha approximation. We will colloquially say that the dual variable YV, quote unquote, pays for the number of solution nodes in its closed neighborhood. For the analysis, let us consider a particular iteration during our algorithm. Let S be the current hitting set. Denote by W the set of currently undominated vertices, that is, not in S or the neighborhood of S. Let S prime be the final solution set returned. This is different from S. By the primal dual framework, it suffices to show that for nodes of W, the closed neighborhood of a vertex V contains fewer than A+1 hit nodes on average. The main idea is that the size of neighborhood of V intersection X counts the number of edges with one endpoint V and the other endpoint in X for vertex set X. In the diagram, N of V intersect X has size 3. Counting these 3 edges incident to V. The summation over vertices V and X, N of V intersect X, counts each edge of the graph induced by X twice, once from each endpoint. Using this idea, we are able to bound the amount our dual variables pay for, that is a summation of the closed neighborhood of V intersect X, by the number of edges of subgraphs of G. From the fact that G is locally sparse, that is arboricity A, subgraphs of G have few edges. This gives us an A+1 approximation. We now get into the details. Let us define S prime of sub W as the solution nodes in W, and S prime sub N of W, the solution nodes outside W, adjacent to nodes of W. S prime sub N of W union S prime sub W are the nodes paid for, that is, solution nodes in the closed neighborhood around any vertex V of W are in S prime sub W or in S prime sub N of W. In this way, we break down the payment of nodes of W towards payment toward nodes of S prime W and payment towards nodes of S prime sub N W. The summation over vertices V of W, N of V intersect S prime of W counts each edge of the graph induced by the vertices W at most twice. This is because S prime sub W is contained in W. So when you go through this summation over all vertices of W, you count each edge of W at most twice, once from each of its endpoints. Then from arboricity A, the number of edges of the graph induced by W is at most A times the size of W. Thus, we get that the summation over V and W, the closed neighborhood of V intersect S prime W, is at most 2A+1 times the size of W. This implies the dual payment towards solution nodes in W is at most 2a plus 1 on average, which gives us a 2a plus 1 approximation if S prime sub n of W is empty. Now we show how to deal with the fact that there may be solution nodes outside W but adjacent to W, and how to improve this analysis to an A plus 1 approximation. For both these problems, we use the minimality of S. For a node U of our solution, we call a node V such that U is the only solution node in the closed neighborhood of V, a witness node for U. Every node of S prime has a witness, as if we did not, then we would delete it, as each node would still be dominated, and we want to delete nodes from S prime if possible. We claim that each node of S prime of W union S prime n of W has a witness in W. The key is that when a node of S prime minus S is considered for deletion, S is still in our solution. Therefore, at this time, the witness for a node of S prime minus S cannot come from S or from n of S, right? These nodes here are already satisfied. They are dominated by a node of S, so they cannot be a witness for a node outside S. Right? Such a node has to lie outside S union n of S, and that is in W. Witnesses pay for a single solution node, which will bring the average number of nodes a dual variable pays for down to A plus 1. Denote by S hat of W the set of solution nodes of S prime W that are not their own witnesses. Here in the figure, the red nodes are solution nodes in W, and the blue nodes are solution nodes outside W. These two solution nodes are their own witnesses, while these this is forms S hat W, these are not their own witnesses. Denote by A the set of witnesses for S hat W, and A tilde the set of witnesses for S prime sub n of W, and just be the remaining vertices. So witnesses pay for a single solution node. For x contained in V, n of V intersect S counts the number of edges from V to X. So we want to bound this summation, which represents the amount that variables in B union S prime W pay. So let's bound this summation, which represents the payment towards nodes in W. We claim that this inequality here holds. And what's it saying? Well, this first term is summing over vertices of B. And what's it doing? It's going through every vertex of B, counting the number of edges that have that as an endpoint, and other endpoint a hit node. So it counts every edge with one endpoint in B, other endpoint in S prime sub W. That is the green edges here, and it counts them twice because there's a coefficient of 2. The second term, it counts edges with both endpoints in S prime sub W, right? Because it's going over nodes of S prime sub W and it's counting how many neighbors in S prime sub W it has. When you put these together, when you put these two facts together, what it means is that in this graph, this left-hand side summation counts the number of edges of this graph twice. And well, let me bound. I want to bound this summation here over nodes of S prime sub W. So first, just a quick remark is that nodes of S prime sub W delete S hat W, that is solution nodes that are their own witness. They're not incident to other solution nodes. So when I take this summation over S prime W, it's equal to the same summation taken over S hat W instead, because the other ones are not adjacent to solution nodes. And what I end up getting is that if I sum the number of neighbors sub n of q intersect S prime sub W for nodes of S prime sub W, I get twice the number of edges in the graph induced by S hat W. So that's these edges here. And when I put this together, when I get this summation here, which represents the amount that nodes of B and S prime W are paying, is bounded by the number of edges of the graph induced by B union S prime W plus the number of edges in the graph induced by S hat W. So here's a diagram. It's this thing here, which represents the dual payment. It's counting the number of edges that are in this graph and the number of edges here. So the two here, the green edges. So that's the payment towards nodes in W. What about the payment to solution nodes that are outside W? Well, the payment to solution nodes outside W is simply equal to the number of edges that have one endpoint in S prime n of W, that is solution nodes outside W, and the other endpoint is either B or it's in S prime W. So in short, the payment to nodes outside W is counted by these green edges here, the edges with one endpoint outside W, the other endpoint in W. Well, when you sum this up, you get that the total amount paid. So here, this is the amount paid to both nodes in solution nodes in W and solution nodes outside of W. What do I get? I get that it's equal to the number of edges on the subgraph of G induced by B union S prime W union S prime n of W. So this graph here, plus the number of edges between nodes of S hat W. So these are these green edges here. Don't worry too much about the graphs. The point is that we've now managed to bound the dual payment in terms of graphs, right? And recall that for the other nodes, A union A tilde, they are witnesses, so they pay one. We know how much they pay. So putting this together bounds the total dual payment, that is summation V and W, this and closed neighborhood of V intersect S prime, in terms of the number of edges of certain subgraphs. And then lastly, use Arboricity A to bound the number of edges in those graphs, in particular, and the number of edges on the graph induced on with vertex at X is at most A times the size of X. And then you plug that in and you sort of do some algebra, and that eventually gives you an A+1 approximation. Right. So I talked about dominating set, primal dual. Well, S is not dominating set. Increment the dual variable to the undominated vertices. Approximation bound V pays for a number of solution nodes that are in its closed neighborhood. We express this dual payment as edges, number of edges of certain subgraphs. And then lastly, we bound the number of edges in the subgraphs using Arboricity A. So that's my talk. Thank you very much for listening.